Hello everyone, my name is Jinming Nian and I'm currently an undergraduate student majoring in physics at UC Davis. My poster is about the energy systematics of the Coulomb effect in gold-on-gold collisions at star. The experiment took place in the star detector of the relativistic heavy ion collider at Brookhaven National Laboratory. Here are some backgrounds of my research. So inside the collider, a gold nucleus is accelerated to close to the speed of light, and it collides with another gold nucleus in a thin gold foil. This image here is roughly what is going on upon collision. And because the bombarding energy is relatively low, protons are stopped in the interaction region due to baryon stopping. Since the protons are stopped, there is a region of positive charge which provides a Coulomb potential. And using the equation for the Coulomb potential of a point charge, we can estimate the size of the fireball. We're using pions because pions are light and are copiously produced. So they are affected by the positive source more evidently comparing to the heavier hadrons. The way we find Coulomb potential is by analyzing the ratio of pions, because due to the positive charge of the source, positively charged particles are pushed to higher momentum, while negatively charged particles are pulled to lower momentum. And pions don't always come in pairs, because in lower collision energy, most pions are produced through delta resonance channels, and there's usually more pi minuses than pi pluses. So analyzing the final ratio of pion by using this physics model, which employs the correct transformation Jacobians for a static sphere and a Bose-Einstein distribution for the pions, we can extract the Coulomb potential. Now we move on to methods. So we start with 268 million events before applying any quality cuts. Then we select the events within the vertex of the target, and we use top 5% most central events. Because the gold nucleus don't always hit head on head, sometimes they only scrape through each other, so that's why we want the most central events. And if you're interested in centrality, feel free to go check out Aaron Poletti's poster for more details. For track cut, we select the tracks that trace back to the vertex. For pion identification, I implemented an n sigma cut of 2 to -2. And n sigma means how many standard deviations a track's dx is away from the predicted band. So you can see this is pion, this is kaon, this is proton, etc. So with an n sigma cut of plus to -2, we can include most of the pions. Using root, we fit the final ratio of pions, pi plus over pi minus, as a function of mt minus m naught, while setting Vc Coulomb potential and Ri, the initial pion ratio, as free parameters, and the pion and proton temperatures are set as fixed parameters. The Coulomb model described the ratio of pions pretty well. And the fit allows us to extract Coulomb potential and the initial pion ratio. And as you can see on the plot on the right, the extracted parameters are consistent with the energy systematics trends. So for a conclusion, the 3-GeV Coulomb potential and initial pion ratio fits well with the world data. But we don't want to just stop there. We want to analyze higher energy data that we collected. However, the immediate problem we encounter as we go to higher energy is kaon contamination. And we will need a more sophisticated method to take kaon contamination into consideration for higher energies. And we are working on it. Thank you for listening. And if you have any questions or if you want to know more about the details, please come to my poster session at 4 p.m. on Friday, October the 30th. Thank you for listening.